If you've done any sort of software development in the last few years, you've probably come across the term CI/CD. It stands for Continuous Integration and Continuous Delivery. It's a way of automating the processes to test, integrate, and deploy your software project. Here's what a basic workflow might look like when you're writing code. Let's assume you're working on a large project with several people and all code is pushed to a repository, say on GitHub. After you write your code and do some tests on your own computer, you feel you're ready to push these new features or fixes to the project repository. If you set up continuous integration, for example with GitHub Actions, you can build the whole project with your changes. The CI tool will also perform any testing you might have included, such as basic functional tests, which are sometimes called smoke tests, unit tests, and full integration tests. You might see CT listed sometimes as a separate concept for continuous testing, but I've included it here under integration. If all the tests pass, you might perform any last quality assurance checks before deploying the code to production. You can also automate this process using tools for continuous delivery. Incremental improvements and testing help teams write modular code, which often results in higher quality code. It also means that bugs are spotted early and often, which results in faster development time, as you're not spending days or weeks tracking down a weird issue that only showed up after checking in a giant chunk of code. These are important processes often used by large-scale software teams, but they can also be extremely helpful for small projects and even in embedded systems. One of the most popular continuous integration and delivery systems is GitHub Actions, as it's built right into GitHub. There are a number of ways to create actions, but a Docker container is one of the most popular. You could simply clone someone else's existing action into your project, like this one from Arduino, but I'd like to start from the basics and show you how to get started by making your own Docker image for testing. Over the next few episodes, I'll show you how to make a simple GitHub action so you can test your code. Even for embedded projects where you might need specialized hardware to test all of the functionality, just being able to show that you can build your project can be massively beneficial for project teams. But to do all of this, we need to go over Docker first. Docker is a platform that lets you run applications inside of virtualized instances known as containers. Let's see how it compares to virtual machines. You might have come across virtual machines before. In a classic virtual machine architecture, a program known as a hypervisor runs other operating systems inside your host operating system. Each virtual machine is a separate instance. This approach offers great security and isolation, as it's very difficult to access the host or other VMs from within a VM. However, full guest operating systems require a lot of memory and computing power. Docker, on the other hand, does not run full guest operating systems. Instead, it relies on containers, which can look and act much like a full OS. However, containers use many of the hardware and low-level drivers in the host operating system to save on resources. A single Docker image contains a number of binaries and libraries for running applications. When you create multiple containers from that image, those binaries and libraries can be shared across those containers. This makes it easy to spin up hundreds or thousands of containers on a single computer. It also means that containers can boot extremely quickly. However, you lose out on some security as your resources are no longer fully isolated like they were in a virtual machine. Docker is extremely popular for building large-scale cloud services for things like websites and applications, as Docker images and containers are portable and easily cloned. It's also a very popular way to create automated testing suites for software projects, as Docker containers can run on a variety of hardware. I'm going to show you how to get started with Docker for exactly that purpose. To begin, you'll want to head to docker.com and download the Docker desktop app for your particular operating system. Once you have it installed, run the application and you should see something like this. Note that you can't work with Docker unless this application is running. There are ways to get Docker working without the GUI, say on things like servers, However, it is easiest to use the desktop application when working with Docker for now, at least for getting started. With the Docker desktop app running, we are going to create a folder for our Docker project. I'm going to keep mine in D projects Docker. Feel free to put it wherever you would like. So I'm going to make a folder here. And I'm going to call this, I don't know, Hello Docker. Let's go into this folder. Note that we're going to start with an existing image. In our case, that's going to be an operating system. That's probably the easiest way to think about this. If you go to hub.docker.com, you can see some very popular starting images. In this case, Ubuntu is very popular along with some of these other Linux images. Note that it doesn't have to be a full operating system like this node.js image. However, for Ubuntu, we will start with this image. Specifically, we're going to use 22.04 since that's a long-term support version. And we're going to create something known as a Dockerfile. Our Dockerfile tells Docker which image to start with and then how to modify that base image. These modifications are performed in things called layers, which essentially does a diff of the file system to create your custom image. So to do that, let's go to our Hello Docker folder. We're going to create a new file, just a basic text file, and we're going to call it Dockerfile. Note that the spelling is very important. You need a capital D. It needs to be all one word and no suffix or extension. This spelling is important because when we run the Docker build system, inside of this directory, it's going to look for this file named exactly like this. If you go to docs.docker.com/engine/reference/builder, or in our case, if you go to docs.docker.com/reference, you can go to Dockerfile reference. Here's where you can get a list of commands that you can use inside of a Docker file. So this is a great reference. We're going to be using run a lot, and you can read all about it here in this reference guide. Let's open up the Docker file using whatever editor you want, and it should be a blank text file. First, we're going to call the from command, which establishes which base image we want to use. This will tell Docker to download that base image. In this case, we're going to download Ubuntu version 22.04. And of course, pound signs or hash symbols are our comments here. The run command essentially performs some sort of command in that operating system. However, it only does it once, and it does so as a layer in Docker so that the file system is permanently changed. That way, when you spin up new containers from this one image, it happens very quickly. To start, I'm going to run apt-get update, which will update our aptitude package manager. I can use backslashes in the Docker file to tell Docker that the command continues on the next line. This allows me to put multiple commands under one run command so that it can all be read very nicely and it happens at once. Generally, you want to try to put as many commands under a single run that you can because remember, each run command creates a new layer. This just helps speed up the whole image creation process. From there, we're going to install Python 3 just like we would on Ubuntu. Then we're going to create a directory to hold our test files. In this case, it's just going to be root tests. Next, we're going to copy in our Python script, which we haven't written yet. We'll call it test.py, and this copy command copies test.py from our local directory, in this case, relative to wherever this Docker file is, into the image. In this case, it will be /tests/test.py. In most cases, when you create a container, you want it to automatically run some application or test suite or something that you've baked into that image. In this case, we will want it to run our test.py Python script whenever the container runs. To do this, we will call the command python3, which is our command, and tests/test.py, which is the argument to that command. Notice that I'm separating these into a list of strings that are enclosed by brackets. These are the arguments that will be passed to the entry point Docker command, so that when the container runs, anything that's found in that entry point command will be run automatically. Sometimes you will see cmd or command also given in Docker files. In this case, the entry point is run, and then whatever is found in the command arguments is passed in to the arguments for entry point. So this will have the effect of calling Python3 followed by this argument, and then something and then else. So it will look something like this if you were to call it in Linux. Note that if you do not give an entry point, Docker will provide the default entry point of /bin/sh-c. So if you just left it like this, command something else, this is what would be called as soon as your Docker image ran. If you didn't have a command, then it would be this. You would do this if you wanted to create an interactive container that you could log into and run commands from the command line. But for now, I'm just going to leave this entry point because we can override it with something else pretty easily. Let's save this. As I mentioned, the Dockerfile is a bit of a recipe to create an image. Now, you can also think of an image as a starting point, as a factory, and this factory will use its own resources to produce containers. So we have to create an image first, and then we can spin up containers, which are the actual instances that run our code or run the code that we've given it. So make sure that Dockerfile is saved and bring up your command line. It's very important that Docker is running in the background. In my case, I've got Docker Desktop, which, as I mentioned, is a good place to start. You can also try typing the Docker command to see if that comes up with something. To build our image, I'm going to call docker build-t for tag, and then I'm going to call it something like my image. This is the name of the image. So we're going to let that build. And you will notice that we do not have test.py because we did not create that yet. So to fix that, I need to create my Python script, which I'm going to call test.py. I'm going to open that. And for our purposes, I'm just going to print the classic hello world. Save that. Now, let's try this again. So docker build-t to tag my image, and then dot tells me that I want to execute this in the current directory, and Docker will look for the Docker file found in that directory. Let's give this a moment to build. All right, with the Docker image built, we can call Docker images to see a list of our images, and here is my image. The other thing you can do is take a look in your Docker desktop under images. You can see here is the image that we just created. Now, as I mentioned, you need to treat these images as sort of a factory. They don't do much by themselves. We use the images to spin up containers or create containers, and the containers are the things that actually run. To make a container, we're going to call docker create. We're going to add the I flag, which means interactive mode. This says to keep the container running and allow interactions, like if we want to log in and do something on the command line. -t is short for TTY. This adds a pseudo terminal for command line interaction. Remember how I said we can override that entry point, and this is how we do it. When we create a container, we can pass in -- entry point equals and some entry point. In this case, let's just run bash. This will run bash instead of running our Python script. Then we should give the container a name. If we don't specify the name, Docker will assign some random name for you. In this case, let's use --name to name it and my-container. Then we need to tell it which image to create the container from. In this case, we only have one image, so it's going to be my image. To list the available containers, do docker container ls-a. And you should see the container ID, the name, my container, and which image it was created from. In this case, my image. Once again, we can go to Docker Desktop. You can go to containers and see the container we just created. Note that the Docker Desktop is a nice GUI. We can manipulate containers, we can create images, create containers, delete them. This is not a bad way to work with Docker, but I'm showing you the command line way in case you wanted to automate this process, and this is always good to know anyway. Note that we can have multiple containers from one image. I could just run that create command again, give it a new container name, and sure enough, we would have two containers from that same image. Just to show you how you can copy in a file into an existing container, let's create another -test.py. And here I'm just going to print some other string to the console. Let's save that, and we are going to go back to our command line interface. And notice that I'm working in Windows here, but feel free to use just about any operating system. This will work in Linux as well as Mac. So I'm going to call docker cp, which is docker copy, another test.py, and I'm going to specify my container, and then I'm going to specify where in that container I want to copy that file, using colon to separate the container name and the location inside the container. So I'm going to do /tests/another -test.py. That will copy in another test to the container. Now let's start the container in interactive mode. We do that with docker start -i for interactive and my container. You should be presented with a root login, and you can see the file system right here with ls. You can also see the tests directory that we created, so let's go there. And sure enough, there's test.py, which got copied in during image creation, and another test.py, which we copied in interactively by using docker cp. If we were to create another container, test.py would exist in that one, but another test.py would not exist if we didn't copy it in manually. Because we installed Python 3 during image creation, we should have Python available to us. So we can run test.py. Sure enough, hello world. And let's run another test.py. This is another test. So you can see Python works. Both files got copied in. One of the files we copied in during image creation, and another file we copied in manually once the container existed. To get out of the container, just type exit. This is a useful way to run programs in a temporary operating system, but note that this can be very dangerous. If you manually copy in a file and make some changes to that file, if you delete the container, that file is gone. So be very careful about when you are working and developing inside of a container. Now let's remove that container. We'll do that by calling docker container rm for remove and the name of the container, in this case, my container, and the container is gone. We can check here, sure enough, the image still exists because that's our little factory, and the container is gone. If you are curious about these commands, head back to docs.docker.com. You can go to reference. This brings you back to that page we were just looking at, and then go to command line reference. And we want the Docker CLI. If you drop down Docker CLI, you can see all the commands we've been using. And in fact, there is a Docker container subcommand with all of those sub-commands. We just ran docker container rm to delete the container. Let's try creating a container again. This time we won't specify a container name, so I'm just going to call docker create and the name of the image. Then we're going to call docker container ls-a to list all of the containers. And you see it gave me the name Loving Feistel. Let's start the container. We will use -i for interactive mode. That way it can print stuff to our console. And we will give it the container name, in this case, Loving Feistel. We run that, and sure enough, that entry point that we specified in the Dockerfile says that the container should run our Python script test.py, which all it does is print out. This -i prints to the console, so if I leave this out, nothing really happens. It just gives me the name of the Docker container that ran, which is why you want that -i argument. Let's go ahead and delete that container. We will make sure that all of the containers are gone. Sure enough, we don't have any. I'm going to use the run command now. So docker run is a combination of create and start. It does both of them at the same time. So it will create a container and immediately run that container. If we want to make it temporary, we use --rm, which says to create and start the container. But once the container is done running whatever it needs to run, in this case the Python script, it should delete the entire container. We do need to tell it which image to use. And there it is. Docker run says create and start, --rm says to remove when done, and the image name. And if we take a look, no containers exist because it was automatically deleted after running it. This is a great way to spin up a container in order to run some code in a very modular way. Note that I can give somebody a Docker image, and they can run it with this run command to run it on nearly any operating system. This is what makes Docker very modular, very portable, and very powerful. Next, we want to delete an image. First, you need to make sure that you do not have any containers for a particular image. If you try to delete an image with associated containers, it will fail. So make sure you delete any associated containers first. Then let's list our images. And to delete an image, you call docker RMI for remove image. And we will remove my image. Call docker images, and sure enough, the image is gone. We are done with another test, so I'm going to delete that so it doesn't clutter up this folder. Then I'm going to create another document. This will be our program under test. Let's create a super simple main.c program. As you can guess, we're going to include our standard input and output. In main, we are just going to print something to the console. In this case, hello from C rather than hello world. And we will return 0. This is important. We want to make sure that we are using the correct return codes in our program. If something fails in your code, then you can return something other than 0 to indicate an error. Docker, or the container in Docker, will pick this up, and we can use that to return a code from the Docker container. And this is how we get to that automation where we can have tests passing or failing. So make sure that you are returning the correct code here. If you just look up Linux return codes, you can find lots of places that will give you the return codes in Unix and Linux. So 0 means okay, anything else is generally an error, and feel free to follow these rules. Usually you'll see 1 for an error. Let's save that C file. We are going to go to test.py and create our compilation and run script. To begin, let's import OS and subprocess. These are packages that come with Python. Keep in mind that you can use any scripting language you want here. I'm just using Python because I'm comfortable with it, but this could be a makefile, this could be a shell script, whatever you want. The idea is to create a test around your main program that will compile it, run it if necessary, along with maybe some unit tests, collect the output of those tests, and pass that back up to the container so that the container knows whether your tests passed or failed. We'll specify our test directory, which is in tests. We'll give it the main.c. This is our C code. Note that you can use something like make if you want to build the full project. I'm just showing a very simple C program for this test. It's usually a good idea to have some sort of timeout. If you don't time out the compilation and the run steps, you might run into issues where your Docker container will run forever. I'm pretty sure that GitHub Actions will time your stuff out. It has a default because otherwise you could just hose their servers by running a bunch of Docker containers indefinitely. So always good to have timeouts for security purposes and to make sure that your code is completing within some sort of allotted time. We'll say that if the compiler doesn't finish within 10 seconds or if the program doesn't run within 10 seconds, we will throw an error. Python can be super wonky with relative paths, so I usually try to work with absolute paths whenever I'm doing things in Python. In this case, let's construct the absolute path to our code. And all we're going to do is combine our test directory or test path with the name of the code file. I'm going to be lazy here and just hard code the name of the output application as app. I like to print stuff to the console so you can see where the steps are happening when you run the Docker container. So in this case, we'll compile the program and we'll print out building to the console. We're going to use the subprocess module to run commands in the operating system. In this case, it's the container. So we're going to call GCC. We're going to pass it our C file, or the location of the C file, and we're also going to pass it the output name of the application. In this case, it will just be tests/app. Similar to what we did in the Dockerfile, subprocess.run expects all of the commands given as a list of strings. We can capture the standard output and error messages by setting the standard out and standard error parameters to subprocess.pipe. If we didn't do that, the output would just be printed to the console. By setting them to subprocess.pipe, we now have them in our return variable that we can access within our Python script. This is a great way to see if the compilation process failed. And here's where we set the timeout. So subprocess.run has a timeout function, and if something doesn't complete within the specified time, subprocess will fail and throw an exception. And this is why it's very important to use try except blocks in our scripts. In this case, all I'm going to do is print the exception to the console after saying error, and I will exit from my program with 1 indicating that there was an error with our script. The Docker container will pick this up and also exit with an error. We can convert the captured standard output to a Python string by calling the decode function. In this case, we tell it to decode using UTF-8. Feel free to do whatever you want with that output. I'm just going to print it to the console. Similar with the error messages, I will also print those to the console. If our return code from GCC is something other than 0, we're going to print compilation failed to the console and also exit with an error. This is where we check to make sure that the program could indeed compile. This is the first major step in our continuous integration testing process. Assuming, of course, that something really didn't fail earlier, but if GCC fails, if you get a GCC error message, it's going to happen here, that something failed. In many embedded projects, you probably won't be able to run the compiled program because it won't be compiled for your particular architecture. It'll be compiled for, say, a microcontroller. However, in other cases, you might be able to run the program in order to do things like unit tests, and this is a great way to do that. Just like we called GCC up here, we're going to call the name of our application, which should be just app, and we're going to capture any output to our return variable so we can access that. And of course, we should set that timeout just in case something hangs the processor. Just like we did with GCC, if there's a runtime failure, we'll print that and then print the exception to the console. And of course, we want to exit gracefully, letting the container know that there was an error. And just like GCC, we are going to decode that output, and we are going to print that to the console here after we have our tag output. If we make it this far, it likely means that all of our tests have passed, and so we show that to the console, and we exit gracefully, providing the return code 0 to show that there were no errors. Let's save this, and let's go to our Dockerfile. We need to make a couple of modifications here. We're going to use the double ampersand to show that we're going to run these commands together. Backslash to show we're going to go to a new line, or that the command continues on a new line. And we want to add build essential, which includes GCC in our image. Just like we copied in our test script, we also want to copy in our program under test, which is our main.c that we wrote a little while ago. And we're going to copy that in next to test.py. Let's save this, and we should be ready to go. Let's come back to our command line interface here, and we're going to build this image. What I forgot here was to tell it where that Dockerfile is and the other files, so I need to specify the current directory. You'll notice that it was much quicker building this time because Docker caches a lot of the files needed for that image. In this case, everything under Ubuntu 22.04. Just like we did before, we're going to call docker run to create and start the container, and then remove it when we're done, and we're going to call my image. If everything goes well, you should see building to show that we are compiling, running to show that we are running the program in the container, the output from that program, which is hello from C, and then our note that all tests have passed. Just for fun, let's do this inside of Bash or some other Linux or Mac shell. I'm going to do this because you can see the return codes from the Docker container, or in this case, the Docker command actually provides the return code from that container. We'll run the same command as earlier, docker run --rm my-image. Sure enough, the tests have passed. I'm going to print to the console the variable ? which is the return value of the last executed command. In this case, this command right here. So when we execute that, you can see it returned 0. That means the command, or in this case, the container, returned with no errors. Now, let's delete that image. We're going to go into main.c, and we're going to induce a very common, very simple error in C, which is to remove a semicolon. So let's save this file, This will create a new image and copy in our bad C file. Now I'm going to create that container with that new image. And sure enough, it failed because I forgot a semicolon. And you can see here, compilation failed, which is a note we made for ourselves in that Python script. So it did building, it never got to run because compilation did fail. So when we print that question mark variable again, it's 1 this time. This forms the basis for building automated continuous integration and continuous delivery systems. Anything that runs our container can now see if it exited with errors or without errors. I hope this helps you get a better understanding of continuous integration and delivery, as well as making your own Docker images. On the next episode, I'll show you how to create a custom GitHub action for testing your code. Good luck and happy hacking!